Hello. So far we discussed different physical quantities like mass, like velocity, like acceleration, and they all represent different features of an object. Uh, Today we discuss another physical quantity which represents the amount of motion in an object. So we have a moving object and we want to measure the amount of motion in it. Okay? So let's assume we have a moving object. It has a velocity and it's moving. And we want to figure out or to come up with a physical quantity that we can measure and we can use to describe the amount of motion in this object. So a very good approach here is to measure how hard it is to stop it. Because when you stop it, you take out this motion. You stop this motion. So if it's hard, this tells us that it has lots of motion. If it's easy to stop it, it tells us that it doesn't have much motion. Okay, so let's assume you have your hand here. And okay, now you want to stop it. Okay, you want to stop it, and I'm just asking you now, how do you know whether it's hard or not to stop this moving object? Okay, what type of questions should you ask me? Okay, so the first question, okay, what do you think? The mass, okay, is it big? Is it small, the mass? So let's say it's 1 kilo, 1 kilogram, and it's moving in this direction. The second question is, how fast is it traveling? How fast is it going? Let's say it's 2 meters per second. Okay, now we can agree that this is enough to describe how hard it is to stop it. So this quantity, whatever it is proportional to velocity and proportional to mass. All right, what if 2 kilograms, it's 2 kilograms or even 3 kilograms, and it's moving towards you now? Now, you can consider it, or you can think of it as 1 kilogram moving in this direction at 2 meters per second, and another 1 kilogram moving at 2 meters per second, and a third 1 kilogram moving at 2 meters per second. So this quantity is the multiplication of these two other quantities, which is mass and velocity. And we give it the letter P, and we call it momentum. Okay, we give it the letter P and we call it momentum. And it's mass times velocity. All right, so the other thing to take care of is that it's velocity, okay? Velocity here. And velocity is a vector quantity. So momentum is just like the velocity, it's a vector quantity, okay? So it's a vector quantity. Another thing is that, so it's a vector quantity. And another thing is that the unit is kilogram meters per second times meters per second. So this is the unit, kilogram meters per second. Now let's talk about stopping this object, okay? So let's start with one of the most fundamental formulas in physics, which is F equals ma. What does that mean? It means if you have an object and it has a mass of m, and if you acting on the object with a force of F, if this mass is big, you will have a smaller acceleration. If this mass is small, you will have a big acceleration. Smaller objects, it's easy to move them. It's easy to accelerate them. They are at rest. It's easy to get them to move and to even move them faster. Bigger objects, it's hard to get them to move and to get them to move even faster. Okay? So acceleration. This is the most important term here when it comes to our class, acceleration. So the acceleration is small. It means we have a small force, which means it takes longer to accelerate to get it, say, to 10 meters per second. Okay? It takes longer to do this. if the force is small. But if the force is big, it's easy to accelerate it, accelerate the same object, and it's easy to bring it from 0 meters per second at rest to 10 meters per second. It's easy. It's faster to do this. It takes shorter time. Okay? So F equals delta mv over delta t, because delta v over delta t, that's an A, right? As we just said, it takes longer to accelerate if you have a smaller force. It takes shorter time to accelerate it, to get it to move, and to move faster if you have a bigger force. All right, so F delta t equals delta mv. This term is called the impulse. Okay, so this term is called the impulse. This term is called the impulse. And delta mv, it's equal to delta mv, okay? The change in mass, the change in velocity. How come the mass is changing? You can imagine a rocket, and this rocket, as it flies, it burns fuel, and it loses. The mass of the rocket decreases because it's burning fuel. The fuel is coming out of here, burned, okay? So it's losing mass. The mass is changing, okay? In this case, the mass is changing, decreasing. Also, on the other hand, maybe you can imagine a snowball rolling down a hill, and it's getting bigger as it goes down. So the mass is increasing here in this case. So this force here can accelerate an already moving object if it's acting at the same direction as its motion. It can accelerate it, or it can stop it, the moving object, bring it to a stop. If it's acting on the object in the opposite direction of its motion, it can even change the direction if it keeps acting on the object, even when it stops. It stops and then keeps acting on the object, so it will just move in the opposite direction. So again, let's imagine the whole situation. So the object is here. If force is acting on this object, if the force is big, it will accelerate really fast. It will become fast in a very short time. It will gain lots of speed, lots of motion, in this case, lots of momentum in a very, very short time. It will be moving in this direction. Okay. Now, if you put your hand here, and once it reaches your hand, if you act on it with like a very big force, you can stop it at a very short time. If you're acting with a small force, you have to absorb it over a longer period of time. So imagine it comes to your hand, it gets to your hand, and your hand gets back a little bit for a longer time before it just dissipates all this motion or takes this motion. So a longer time, but a little force or a smaller force, it's easy to stop it this way. Imagine throwing something big at you, and you just your hand gets back with it, okay, it's absorbing the motion over a longer time. You don't have to exert a lot of force in this case, but if you want to stop it immediately, it hits your hand and stop and fall, it takes a lot of force. So F delta T equals delta mv, okay, the change in momentum. If you keep pushing in this direction, even when it's even when it stops, you can even force it to move or make it move in this direction. Okay, you can change the direction. It came to you in this direction, but you reversed its direction. Okay, so again, F delta T, this is the impulse, equals delta mv. And the unit of impulse is Newton second, or the same as the momentum, kilogram meters per second. Okay, it could be any of these. All right. Now I have a problem here. A car of mass 600 kilogram is moving at 15 meters per second. Calculate the momentum. So this is the first question here. Calculate the momentum. The momentum P equals the mass times velocity. Okay, so P equals 600 times 15 equals 9,000. And the unit, kilogram meters per second. The second question, the second part is the driver accelerates gently so that a force of 30 Newton acts on the car for 10 seconds. Okay, so the car was moving at this constant velocity, and then he accelerates it like the gas pedal, and there is a force from the engine, and it accelerates a bit. The force from the engine acts for a certain time. So this is the impulse, force times time, the amount of time, okay? So the impulse equals F delta t. In this case, 30 times 10 equals 300 Newton second. Next, calculate the momentum of the car after the accelerating force has acted on it. Remember that the impulse itself is the change in momentum, okay? The change in the momentum. So in this case, the momentum increased, and this increase is actually the impulse, all right? So you can find the final momentum in this case as the initial momentum plus impulse. That means 9,000 plus 300. So the final answer is 9,300 kilogram meters per second. So this is the final answer, okay? All right, so that was it for today. I hope you liked today's class. If you like it, please leave a comment, like, subscribe, and maybe even share with your friends. See you again next time, and yeah, bye.